Now let's look at the conductive segment, or the axon. We can have two ways that our action potential can travel down the axon. There's continuous conduction, and then there's saltatory conduction. Saltatory means jumping. With continuous conduction, the charge that we have is going to open the voltage-gated channels, which allow the charge to enter, and then that change in electricity then spreads to the area next door and opens more channels, and so on and so on. Saltatory conduction occurs on myelinated axons, and here's where myelin comes into play and is able to allow us to conduct our signals much quicker. The action potentials only occur at those nodes of Ranvier. After sodium enters at a node, it starts a positive current down the inside of the axon's myelinated region. The current becomes weaker with distance, but it's still strong enough to open up our voltage-gated channels at the next node. The myelin basically insulates and helps kind of protect and isolate that signal so that it's strong enough to bypass all of that area underneath the myelin. Then we get a full action potential occurring at the next node of Ranvier, and the process repeats. But we've already covered a massive amount of distance, a whole millimeter or so, and so saltatory conduction is around 20 times faster than continuous conduction. On the left, we have continuous conduction with our sequential opening of sodium channels, and then as the sodium rushes in and changes the electricity, we have the opening of the electrically gated channels next to that. The sodium rushes in there, and that causes the electrically gated channels next to that to open. Whereas with our saltatory conduction, we have our depolarization on our node of Ranvier, and then the positive signal is able to travel underneath the myelin over to the next node of Ranvier, where we open up our channels. It's almost like our nervous system is able to ignore all of the axon underneath the myelin, and in effect making the axon much, much shorter, at least physiologically. Once we finally arrive at the synaptic knob, calcium is then going to diffuse into the knob. That action potential was able to open up electrically gated calcium channels, and we've had calcium pumps the whole time establishing a resting gradient where we've got a lot of calcium outside of the cell, and so that calcium then just diffuses in following its concentration gradient. The calcium then binds to a protein called synaptogamin, which allows the synaptic vesicles to bind to the outside and through exocytosis release their neurotransmitter. The neurotransmitter then can diffuse across the synapse and plug into our postsynaptic receptors, and then either, remember, cause an excitatory or an inhibitory stimulus to happen. So here's our chemical synapse. Our action potential zips down the axon at 200 miles an hour, opens up those calcium channels, calcium diffuses into the cell, binds to the protein synaptogamin, and allows those vesicles to bind to the outside of the terminal and release their neurotransmitter through exocytosis. The neurotransmitter then diffuses across and plugs into ligand-gated channels. So the graded potentials are the smaller, quick changes that we're going to have on the receptive area of our neuron due to the ion flow through chemically gated channels. And these ion changes can be positive or negative. Because the changes are graded, they have a larger or smaller impact on the neuron. Action potentials are different from graded potentials. They occur only on the axon. They're due to the sudden inrush of sodium through voltage-gated channels, and then the resetting of that, the repolarization of opening electrically gated potassium channels. And action potentials are always all or nothing. If you reach threshold, then you have an action potential. It will race down the entire axon to the very end, or not, one or the other. Now, the conduction speed of an action potential depends on axon diameter and myelination. Thicker fibers conduct faster than thin ones because thick axons offer less resistance to current flow down the axon because they have more channels available in the same amount of space, and so we can push more ions through at any given time. Myelinated fibers also conduct much faster than unmyelinated ones. Taken together, our fastest neurons are going to be the ones that have thick axons that are heavily myelinated. Our slowest neurons are going to be small axons that are unmyelinated. So nerve fibers have groups to them. Group A, the conduction velocity is as fast as 150 meters a second. These are large diameter myelinated fibers. Most of them are somatic sensory neurons. All somatic motor neurons fit into this category. And then group B fibers conduct at about 15 meters a second, which is 10 times slower. And then group C at 1 meter per second. For instance, the neurons that carry pain signals. Those pain signals travel about 1 meter per second. You've had experience with this. If you've ever cut yourself or damaged yourself, say you're in the kitchen with a knife cutting and you look away as you're cutting vegetables and you feel your hand roll oddly and you know you didn't do it. So you look down and you see the knife and you see the blood and you have enough time to think, oh crap, I've cut myself before the pain hits. That's because the neurons taking the information on the positioning of your hand are group A neurons, and the ones carrying the pain information are group C. And so it takes longer for that pain signal to get to your brain. It's persistent, I'll give you that, but they are slower. Even though the impulse amplitude of neurons is always about the same, remember it doesn't matter how much stimulus they get, they're always going to go up to about plus 30. If we increase the frequency of the stimulus, then our brain encodes that as a stronger stimulus because the neurons are firing more frequently. For instance, bright lights will cause faster firing frequency on the optic nerve than dim lights will. When motor nerves fire at a faster frequency, it causes muscles to generate more tension. For neurons that can use different neurotransmitters, the firing frequency can influence the type of neurotransmitter that is released.